Yes, sir.
Thanks. Mhm. Okay, so I think we can get started. Okay, so good morning, everyone. So it's my immense pleasure to introduce Mr. Debdoot Mukherjee. He is the Vice President AI at ShareChat, where he leads a team in the area of feed relevance, recommendation system, and multimodal intelligence. Debdoot has over 12 years of experience in building innovative AI product in social, mobile, e-commerce domain. Prior to ShareChat, Debdoot was leading the AI team at the Hike Messenger, where he created several novel applications around conversation modeling in Indic languages, image video understanding, massive scale social graph mining, etc. Previously, he led AI program at Myntra for applications such as personalized search, product discovery, marketing, and merchandising intelligence. Prior to Myntra, Debdoot worked at IBM Research, where he investigated problems related to enterprise search and information extraction. Debdoot is a gold medalist from IIT Delhi, where he graduated with a master's degree in computer science and engineering. So it's my immense pleasure to welcome Debdoot, and we are very, very exciting about your talk. So over to you, Debdoot.
Yeah, thanks, Rajiv. I'm equally excited to talk to this audience today on a topic that's we are doing quite a bit of work, but more importantly, it sort of it is a topic which has an immense amount of potential to bring an impact in how we understand the world around us, and of course, in the context of social media, it is a topic which is extremely critical to how the platforms operate. So what I'll do today is I'll give you a brief overview of ShareChat and some of the multimedia applications therein. More importantly, and the applications are not specific to ShareChat. Pretty much any social media platform would care about these applications. So these are general in that sense. And then I'll sort of slip into a little bit of a tutorial mode where I will look at the field of multimodal learning, starting with like how it has evolved, what are the current hot topics, what are the current applications being worked on, and touch upon this topic of how do you create multimodal representations of any piece of content, right? And finally, I'll touch a little bit deeper into video understanding, because video understanding is video by definition is multimodal in nature, and this is one of the tasks where sort of multimodal learning comes out in its full glory. So we look at some of the challenges in video understanding and what kind of approaches are coming up in literature and so on, right? So that's going to be the agenda for the day. So without further ado, let me just dive in with an overview on what ShareChat is. Not sure how many of you are familiar with the platform. ShareChat is India's largest non-English social media platform. So it's an application which works something like this. You install and log into the application. You would be presented with this kind of a screen that you have on your right, where you select your language. And the most important thing here is you cannot select English as a language. It needs to be one of the 15 Indian languages. And once you select that language, you land on a feed, which is a never-ending feed of short videos and images, right? So that's pretty much it, what the application is. And we've been growing pretty rapidly. Today, like we've crossed around 160 million monthly active users with a lot of time spent and content viewed and shared on the platform, right? So like one of the key differences with if you look at ShareChat, and one of the unique things about the platform is really the spread of topics and the kind of topics that trend. Being a language first platform, a lot of the audience that we have come from like tier 2, tier 3 cities, towns. They are a language first audience, needless to say. But they're very, very unique in the spectrum of topics that they care about, right? So ShareChat became famous as one of these platforms where you can find high quality shareable content. So if a lot of you are being your WhatsApp folders are bloating up with forwards, and especially in Indian language forwards and on greetings and these good morning, good night messages. Um, with a high degree of confidence, I can say that the source of many of those pieces of content is ShareChat, right? And that's how like the platform became famous. But then, if you look at ShareChat today, we have everything from astrology to devotion to agricultural content, like to, of course, entertaining content, um, motivational quotes, right? It's extremely shareable. Um, Educational content. So education, when you look at the ShareChat content, it's not what you would expect in Coursera. Rather, if there is a bank clerical exam, what are cheat sheets that would make you pass those exams? So that's the nature of the content. It's very different and very unique. Something which you would probably not find in most of the Western platforms, even if that kind of content exists in some of these Western social media platforms. Um, they are probably they would not trend as much as they do on ShareChat, right? So this is one key thing, that our content is spread over this long tail of genres, right? And like the product essentially is that if you log in as a user, you see a feed, this never-ending feed, and it sort of shows you just what you need at all times, right? So that's driven by AI algorithms. One of the key differences, like any feed on any social media platform, is driven by an AI model which does the ranking. But one way that the ShareChat feed sort of sets apart compared to many of those is most of the platforms which got developed in the West, there you either you search for it, which is search is not a behavior which comes very naturally to the audience that we are talking about here, our target audience. And the feed works much better, but when it comes to feed, it's not a follow based feed, unlike many of the erstwhile platforms, right? And follow as a construct does not work well for us. It's not that we want to do something jazzy and we sort of created an AI first feed. If you look at the kind of content that I just described in the previous two slides, you would realize that like this content is being created by an ordinary user, right? Who, when you walk into the platform, you would not know who's the user who creates the best of the good morning messages, right? So hence, when you walk in as a user, your propensity to follow people will be much lower than in other platforms, where if you find a celebrity or if you find a politicians or you find a thought leader, you know that person offline, and hence you would, if you follow him or her, you would understand what kind of content you'll get on your feed. So follow comes very naturally in some of the more popular social media platforms, not so much in ShareChat. And hence, our feed is entirely algorithmically driven, right? We start off showing some popular and diverse content, and then as you go forward, you get more and more sort of personalized content, right? And which is catering to what kind of content that you like and engage on the platform. Okay, so we cater sort of multiple distinct needs. I talked about it being a platform to share, like discover shareable content. It's a platform to be entertained, watching short videos of music, dance, and these categories. It's a platform to stay informed. Like a lot of the um audience that we have, they don't go to a conventional news website to consume news. Their knowledge of what's going around in current affairs comes from a platform like ShareChat by consuming some of these news, but presented in a meme-like format. Right? And it's also a place to interact with like-minded community, like-minded sort of people. So there are these mini communities, which like, and thousands of them, which have come up in ShareChat, where people sort of interact with like-minded users who have a common taste in content. And usually this taste is very, very niche, right? So just to give you an example, we have a group in Kerala which sort of gets together every Sunday to read sections of the Bible, right, and conduct a mini mass. So this is how, like across India, people are coming together, uh, bound by common interest in specific niche topics in content. And this is how ShareChat is a platform which is enabling some of these needs. Right? Okay, so on to multimodal intelligence, which is sort of the focus for the talk today. So multimodal intelligence is all about understanding content from different modalities, visual, audio, and text. But like, what are the key application areas where multimodal intelligence gets applied on ShareChat? And for that matter, most other social platforms, I would imagine like these are the business objectives and business use cases where multimodal intelligence plays a big role. So the first one is content understanding, right? So the goal is, uh, okay, sorry. The goal is really to understand content in the same way as a user, right? And we'll talk much more about this particular topic today. Second is trust and safety. It's imperative to keep every piece of content on ShareChat and monitor so that you ensure that it's safe for every user, right? And also to weed out low quality spammy content, right? And duplicate content and so on. Okay, so just give you some examples so that you start getting a flavor of what kind of content exists on ShareChat and how can machines interpret them and how easy or difficult. So these are fairly straightforward use cases. If you look at the picture on the left, that's on this tag called Mehendi Design. And from the visual cues, you should be able to teach a machine that, okay, this is Mehendi, right? Good morning, good night. Many cases, the text is right up there, so it's straightforward. Someone like a cricketer, Rohit Sharma in this case, like if you do a good job of face recognition, again, this is a very straightforward example. But then the things could become much more subtle, right? So, for example, you have patriotic content where there is a piece of text. In this case, there's a giveaway because there's a person who's carrying a Indian tricolor, so you'll probably sort of guess from that. But then otherwise, you would need to process the text, and the quality of your NLP would dictate whether you are able to get this prediction correct, right? Another one of similar nature for in the friendship category, right? So is this content about friendship? The last one on the screen is on, like, it's a puzzle. So again, based on text processing, you would need to figure out whether this is a puzzle or this is some other content. So these are some examples, and like some of the topics that I showed were sort of evergreen. So you'll tend to get a topic on those pieces of on those topics every day. But then there are much more temporal topics as well, and IPL is of course the flavor of the season. So here are a few examples. Delhi got beaten by, or Chennai got beaten by Delhi, right? So it's a very temporal meme. If you read the text, there's no clear reference to IPL or teams, but the fact that there are these Delhi and Chennai, and from the context that's sort of ongoing, you'll figure out that this is the case. And here, like, even though it's Virat Kohli, probably your face detection would not get it correct because it's a little bit on the harder side, right? So So how do you get some of these content correct, and also in topics where you're come like the topics themselves are very, very new and temporal, right? So you can't afford to create a training data set and train a model, and then like by the time you do that, your content will go out of trend, right? So your systems that do content understanding should be very adept at catching these trends, and there will be some topics which will be evergreen, and you can afford to train models on them with a lot of label data, because those trends don't go away. And then there will be these temporal trends which you need to deal with in a different manner. Okay, so then the other use case I talked about, trust and safety. NSFW content detection is on that. So we have different categories of content which is potentially not safe for the users, and here are some of the categories that I've listed on the left. And usually the way, like all of these models are again multimodal, right? And they also take into account other kinds of features on like historically, is this creator being a bad actor and so on. And all of these models, because it's so very important to keep the platform safe. Usually it's a combination of a machine and a human workforce that does moderation. And the way we tend to set it up is in an active learning kind of loop, where the machine is continuously getting better at delivering precision on a variety of examples, and the harder examples get looked at by human beings, and moment that gets reviewed, that sort of the machine catches similar examples and sort of inculcates that learning for future, right? Okay, so this is another interesting one. So we call them engagement bait. So these are low quality platforms. So in most social platforms, the ego metric for a creator is that they want shares and likes and so on and follows, right? So people tend to put in such kinds of content like to really trick you into liking the piece of content, and like in many cases this could be also getting to the extent that you're almost doing a little bit of a blackmailing at some level, to say that, okay, if you don't follow this, or if you don't like this, bad things will happen, or if you like this, fantastic things will happen, and so on. So it's important to catch these baits, and this is another little application of multimodal learning. Okay. So before we go into multimodal learning and some of the theory, let's look at unimodal representations. And like if you look at the kind of content that is there on each of these modalities, visual, audio, and text. And context is actually like slipped in that as a fourth one. There's context on the creator, context on historical trend about the topic, maybe location is a context. So that lends another dimension to of modality, so which is important for many of the models. But let's look at visual, audio, and text, and let's look at what are some of the base representations that we create um, that will be then used by multimodal networks, right? So what do we do for visual representation? So visual representations, for any image or for any frame in a video, you would create a visual embedding. And the starting point for these models are these pre-trained models on your favorite CNN backbone, which is trained on image classification tasks on datasets such as ImageNet or OpenImages, right? And like, so that works, that gives you some degree of visual similarity. You can find out visually similar content, especially like if it is rather simple and it sort of relates to categories that it is present in ImageNet, it works quite well. But then our content is quite different, so like fine tuning should definitely help. right? And one of the concepts which got talked about in a paper called by Facebook is this aspect of weakly supervised pre-training on a very large scale data set. So in this particular paper, they showed that if you train like pre-train on a set of Instagram tags, which could be noisy, but it's a very large data set, some 3.5 million data set, then the performance on ImageNet increases significantly, right? And so that's what we tend to do as well. So we have lots of content, but the tags on them are pretty noisy. It could be as the noise rate or the incorrect tags could be almost around 30 to 40%, right, on ShareChat. So it is noisy, but what we notice is even on that noisy tag data set, if you fine tune, you get much better models. The other concept which has come along lately is that this notion of contrastive learning. There's this paper from Google team, SimCLR, which said which demonstrated how you can augment the image, right? And with multiple augmentations of the same image, you can train a network in a self-supervised manner, right? And that also, again, because we are a platform with a lot of data, but collecting labeled data is always costly. Any approach which can work in a self-supervised manner is of course attractive to us. And in this case, we got some good gains by training self-supervised learners on different frames of the same video, which are essentially talking about the same concept, but maybe put in a slightly different way, right? And that tends to be a good data augmentation technique. And then there are other derived visual concepts, right, which are also important to extract from an image. So one of the examples is faces carry a lot of information, right? So as we saw in some of those examples, if you pick out that, okay, this is Virat Kohli, your content understanding work is half done, right? So hence we also sort of use these architectures like FaceNet to extract faces and map them to known entities within the platform. Okay, so that's about visual. Quickly, I'll go over audio representations. So there are two ways to sort of infer information from audio. One is from the frequency kind of information. So in this case, like we train a network called VGG-ish, right, which trains on this log-mel spectrograms. And there is a large-scale audio data set from YouTube. And that is one representation that we work with for audio. And the other thing is we transcribe audio to text and then use text representations on top of it. Again, doing audio transcription for a lot of the Indian languages, especially the low resource ones, is still not like we've not gotten to very high levels of accuracy. So a lot of work that's pending to be done there. Okay, so on to text. We have the one thing which stands out for text in a platform like ShareChat is we have these 15 different Indian languages, right? And many of them are actually low resource languages, right? So how do you deal with them is one of the things that we need to be aware of. So we start off with these pre-trained sentence transformers, which are cross-lingual models. These are thankfully available for a lot of major Indian languages trained on large scale data sets. They perform quite well. And then you would tend to fine tune it on ShareChat data. And for low resource, one of the tricks that we do is we tend to, a lot of the low resource languages also share script with another Indian language. Even if they don't, we tend to transliterate them into the Hindi script, and then we train a model, cross-lingual model on that text corpus, which is trained on Devanagari, where the corpus is much larger, right? And it works surprisingly well because some of the word roots in many of the Indian languages they sort of go back to a common word root in Sanskrit, and this approach tends to work well. Okay, so one of the things that we needed to do to actually get text, right, is OCR, right? Because our platform has images and short videos, that is largely it. So in order to get to the text, we need to do OCR because the text is embedded in these images and videos, right? So we have developed a OCR system which does quite well, which is focused on dealing with index scripts and decorative fonts, right? Which are two problems these pose challenges to most of the proprietary OCR systems. So we did sort of resolve some of those challenges, and I'll quickly talk through some of the steps in our OCR pipeline. By the way, this is something which will be open source soon. So if some of you guys want to use OCR in an Indian language setting, do look out for this particular system which is coming your way. Okay, so essentially, let me sort of go. There are multiple stages in the OCR pipeline, starting from text detection to script identification, and then recognizing the text, and then putting it all together. So I'll go through one by one very quickly. So text detection. Is something that we use network from East, that's called East. It came through a couple of years back. It has simplified. One of the reasons for choosing East over other alternatives is it's a very fast and efficient approach. And it is fast and efficient because it is very simple, unlike some of the other conventional OCR backbones. It has only two stages. It has a fully connected, fully convolutional neural network, and then which gives you these candidate bounding boxes, and then there's NMS-based merging on those. Once you detect the bounding boxes, which contain text, then the next thing is to pass it through a script identification module, which identifies one of the 12 index scripts. And the reason we need to do that is the next step of text recognition is actually trained per script, right? So text recognition, we use a network called Aster, which again came in 2018. One of the things that Aster does is that the first step in Aster does a rectification of the text, right, using this TPS transformation. So you see this curvy little text on the top of your screen, siyasat in this case in Hindi, and that is straightened by this rectification network. So that's the first step in Aster. And then once you have a straightened text, they go from image to text in a sequence to sequence fashion, right? So that's what Aster does. The next step is once you have these text segments identified, you would still need to stitch them together, right? Because you have these different segments, and in this case, if you see, like it's not always straightforward to just go from left to right and top down to get a piece of text which is coherent, right? Because you have the alignment is of all kinds of different forms in the images that we have. So what we do is we have a neat little technique where it looks at like the bounding boxes that are detected. It looks at the adjacent bounding boxes, and wherever there is a nearby box, we tend to sort of connect those two and create a graph out of it, and then run strongly connected components on that particular graph to weave out the boxes which are related, right? And that's how from word level. So by the way, I forgot to mention, our text detection works at a word level, unlike at a sentence level in many of those OCRs that tend to work well in the set of images that we have. So this is a way to connect these bounding boxes which are there at a word level to stitch them together to create a text segment, right? And then there is one stage in the pipeline which is dedicated to removing some of the texts which are really not important to the rest of the text which is present in the image. So in this case, this is like a logo which is there, or a watermark, and many of the watermarks have text which sort of add a lot of noise to the overall text that you want to extract and then process in your NLP pipeline. So it's important to get rid of these watermarks and spurious pieces of text, and we have a stage in the pipeline dedicated to that. Okay, so with that, I'll move on to multimodal learning. I'll start with the definition. So like multimodality got researched, it sort of was born in the domains of psychology, where people were studying how humans, machines can interact in the same way as humans, and the key signals that humans have to process information are the sensory signals, our five senses. And people have also talked about attention, memories, and preferences, which are sort of created over a period of time as additional sources of information. So the definition of multimodal learning could be really simple. Like any system which processes more than one pieces of information in such modalities is sort of a multimodal system. There's an interesting little YouTube video where there's a commentary on how the definitions could be confusing, where they take this example of, let's say, a picture of a cat presented in RGB and in infrared format. For a human being, they'll process these two images very differently, right? But they are not conveying any additional information from a machine's perspective. Right, so they've tweaked the definition a little bit to say that we need an information-centric definition to deal with some of these. But let's go over that. So this is one of the effects, and I understand that the audio will not work. So you'll not get too much of what's going on here, but for those of you you've not sort of heard about this particular term, McGurk effect, it talks about essentially this is what happens here in the video. There's a person who's talking and he says ba ba, and if you sort of look through the video, the audio always says ba ba, right? But when the person is saying something like va va, and you are looking at that video, you would tend to sort of recognize the sound as va va, right? So it's about how in our brain audio and visual signals are processed in a combined manner, and hence in this particular case, visual information changes how you interpret the audio information. So this is very interesting, and it led to some of the early applications in multimodal learning. One of the first examples was in the domain of speech recognition, where people sort of had a lip reading pipeline, right, which sort of interprets the facial lip movements in a video. And when they combine that with audio features, the quality of the overall ASR was much better, right? And then so that was the start in the 1980s. I just wanted to make a point here that even though multimodal learning is a hot topic and we are saying that this is a booming field, the concept itself is dates back to like 80s and 90s, and it's not new in general. Of course, the techniques that we are using in the deep learning era today makes a world of difference, because the accuracies that we are seeing could not be imagined even 5 years back, right? So Okay, so a lot of work happened in 90s in the field of multimodal content analysis, scene segmentation, genre classification. These are classic tasks which got worked upon. In the first decade of this century, we had these multimedia retrieval challenges. Trek, which runs a famous sort of competition in the text information retrieval world, also had something similar for videos. And all of these were tasks which got worked upon. And that's when the multimedia sort of technology specifically for information retrieval sort of got worked upon. And today, if you look at the tasks that where multimodal learning is playing a role, it's sort of it's a very diverse array and some very interesting examples there. Like people are, especially in the synthesis bucket, people are creating faces from voices, right? So just by understanding the voice, you will create a face and figure out how that face looks like and what kind of emotions and so on. So it's very interesting stuff in the synthesis domain. You have event detection, where of course a lot of these visual grounding and action classification, very popular tasks which are getting worked upon. Emotion recognition. I think here we need to do more. One of the things which is a setback is I don't believe we have good enough emotion recognition data sets, and especially at large scale. But this is something which actually is if it works well, it could be a very useful thing for social media platforms, um, especially for the kind of tasks that we are talking about today and content understanding and so on. If you can detect the emotion, you can go a long way there. Um, and then, of course, media description, a bunch of tasks, and every 6 months, you're sort of having very significant improvements to the state of the art here. Okay, so very quickly, what's a multimodal representation and what's the purpose? So essentially, you have the same concept, which could be described in different modalities, using different modalities. The purpose of a multimodal representation is to narrow the distribution gap in a joint semantic subspace, right? So, but at the same time, you should keep your modality specific semantics intact. So there are complementary pieces of information which are being conveyed by the image and the text and the audio. Those need to be intact, but at the same time, if there are similarities, then if you can sort of project into the same space, then that is what the intention of multimodal representation is. Right, so there are a few different orthogonal approaches of representation learning. First one we call joint representation, where essentially the idea is that you project these unimodal vectors into a shared semantic subspace, right? And then you can concatenate in that subspace and then use that for that encoding for the downstream task. Then there are these coordinated representations where, unlike projecting them into a common subspace, the representations of the different modalities are still separated, but they are constrained by like certain kinds of constraints so that they are coordinated in some sense. And then there are these encoder-decoder networks which get used in a variety of translation tasks to map from one modality to another. Right, so very quickly, joint representation, we sort of describe the simple concatenation approach. There are other approaches around jointly training these autoencoders with audio and video, where you project audio and video inputs into a shared space and then try to reconstruct the audio and video, and that sort of leads to these the features from the audio world and the video world interacting in this shared representation space, and you get much more robust representations spanning audio and video signals. right? So, and then people have gone for more sophisticated approaches. If you just look at the previous network of a simple concatenation, you are only sort of taking linear interactions between audio and video. How can you sort of get more expressive power? So this is one technique called bilinear pooling, where essentially you try to learn from the outer product of the unimodal vectors to capture all kinds of interactions between the features from the two different modalities, right? And of course, this is a very expensive thing to do to compute outer products, so people have proposed more efficient approaches to do this. VideoBERT is one technique which, like, if you, I'm sure you guys sort of follow the proceedings of CBPR and ICCV. If you look at the last few years, like I just sort of run out of count of how many XYZ BERT papers have been created. But anyway, so BERT is definitely a technology which has changed and made a lot of things possible. And in this case, for VideoBERT, for video understanding, this is one very nice way of creating a joint representation of video and text. Actually, in this case, they transcribe the audio into text, and they learn these visual tokens with the help of an S3D network, which sort of processes the clips from a video and passes it through an action recognition backbone and creates a visual token. And then once you have these, you can pass the video tokens and the audio tokens together into a BERT setup, which is trained using this clause test, mask out a few of the tokens, and you try to predict those mask tokens in a self-supervised manner. And this has been very successful in understanding videos, especially some of the test sets that they worked with, these cooking videos from YouTube, and at least on that set, it's very effective. Okay, so we spoke about coordinated representation. For the sake of time, I'll just speed up a little bit and rush through some of the slides. I think you've got the broad idea here. One of the things is, how do you coordinate representations obtained from two different modalities, either using a similarity metric like this one. Uh, People have shown that, okay, the vector space arithmetic, which gets talked about in the text world, also is present in an image world, where you can do all of these transformations to create a representation similar to a red car uh, from a blue car by just doing minus blue and plus red, right? And then, like, this is another way of doing coordinated representations, where the constraint that you apply is that the projected modalities are maximally correlated in this particular space, right? So you choose, like, this is what you use to coordinate the two different modalities. Okay, so we've talked about this. Let me get to holistic video understanding. So the question is, what matters in a video? Again, you would not sort of hear the audio here, but maybe you can watch the visual thing. So it's basically a Michael Jackson song. So what matters in this particular um, video? So is it a group of men walking? Is it the door opening? Is it the man shouting? Is it the emotions? Is it the pop song? Is it the 80s song, right? So if you're interested in this song, you'll probably interested in other songs of that period. Or is it just Michael Jackson, right? So like, there are all of these dimensions which are important, right? And which need to be captured to really create a representation which would effectively summarize how humans perceive a video, right? And can we do a good job with our video representations? And so how do we learn them? So learning multimodal representations are essentially, these are two tasks that we use internally, and also have been talked about in the literature. So you train multimodal representations to create similar representations of videos which have related semantics. So what do you mean by related semantics? They are likely to have the same hashtag, right? Or to be watched or liked by the same set of users, right, on the platform. So these are the signals and these are the data that you use to train video representations. So what are some of the related tasks? YouTube 8M, this was a famous challenge on a very large scale YouTube data set, spanning like almost like 3,800 classes. And a lot of the video representation networks actually, which are being used in the industry, got developed as part of that challenge and like got to the top of the leaderboard in that challenge. I'll explain one such network shortly. And then this is a recent thing which has come up this year on holistic video understanding. What they talk about is YouTube, of course, it's just one class, right, and one type of label, which is similar to a hashtag in some sense. There could be multiple labels for video, but it's kind of a topic. But what holistic video understanding is saying is, can we separately have different types of labels, right? So they talk about like action, concept, like which is similar to emotion in some sense, but it can transcend to other dimensions as well. What is the object that is being portrayed in the video? What's the scene or the background? And other kinds of attributes of color and so on. Right. So like they have a large scale label data set on this one. And the idea is if you can sort of predict all of these attributes then through a single representation, then that would lead to high quality semantic representation of the video, right? So the other thing that I talked about is also the two ways to sort of learn a representation, at least using our kinds of data in a social media world. One is predicting these topics. The other is something which is called like how can you learn from the co-watch behavior or user interactions on the platform. So the key idea here is that the highly co-watched videos need to um, appear nearby in the embedding space, right? And there's this paper from Google YouTube team, Collaborative Deep Metric Learning, CDML, which is sort of, it's a simple sort of triplet loss where they have three videos, anchor, positive, and negative. The positive is sampled from videos which are highly co-watched with the anchor, and the negatives are randomly sampled, and you train a triplet class and you get to these embeddings, and it works pretty well in practice. One of the key things here is to actually sort of have very clean um, positive labels, right, as well as hard negative labels, right? So how do you do that and create such a data set is where the trick is. And as like your quality of representations would be pretty much a function of how accurately or how effectively you can get the good positives and the hard negatives, right? Okay. So one of the important things, so we spoke about unimodal representations, but we like did not consider how can we go from, let's say, a frame level embedding to a video level embedding, right? And that's where this concept of spatiotemporal feature learning comes in. And like in a video, you need to sort of like the video representation that you would learn that needs to capture spatial information, which is appearances of objects and scenes and all of that. But then you need to capture the temporal information and process like how correlation and causation through time, your features from like one frame and a following frame need to interact effectively. And so you need this temporal aggregation on top of frame level embeddings, right? And that we need good techniques to be able to do that. And like there are techniques, and so there are these 3D CNNs which are quite effective, especially at least in the realm of action recognition. They've proven to be effective. But one of the things about 3D CNNs is the complexity of training such networks as well as running inference is quite large. So people are looking for ways on how do you do effective spatiotemporal feature learning in efficient and scalable manner. Right? And so like a little bit on approaches to counter this particular problem that exists. So the naive baseline is, of course, you take all the visual embeddings for the sample frames, as many frames that you can probably afford to keep, and then you pool the visual embeddings. Of course, this is quite naive. So the better approach is can you train like encode the video embedding through an LSTM, which takes in these frame level embeddings at each time step. And what people have done is, instead of working with frames, it's better if you do the temporal aggregation at a clip level. Right. So the key idea, and this is presented in this paper S3D, is that it's not as effective to temporally aggregate low-level information, uh, but it is much more effective if you have a semantic representation and then you have a temporal aggregation at on those semantic representations, right, which are like higher order semantics than low-level features. And so what they tend to do is they have these clips that are extracted. These are short sort of sequence of frames, and they run it through an action recognition backbone on this kinetics data set, good 3D CNNs which are trained on that. And you get that, and then you can then do the temporal aggregation on top of these frames in using different techniques. And one such technique is called gated NetVLAD. This was one of the winning solutions to the YouTube ATEM challenge, and is being widely used in the industry today for video understanding. So there are two distinct sort of things that this paper talks about, like concepts. So one is learnable pooling and the context gating. So I'll go through one by one. So the first is the learnable pooling. Okay, before that, like for those of you who are not sort of fully familiar with the concept of this VLAD, which is vector of locally aggregated descriptor. So like in, let's say, the prior to the non-deep learning era, right, in the olden days, to say, the way a lot of these information retrieval tasks were done was using, they tend to create for, like, and this is true for images as well as videos, they have these code books of visual words, right? And an image or a video was represented as a histogram, like in a bag of words model, histogram on that particular code book of what are the visual words that they have, right? And then VLAD is a slight improvisation on top of that, where they consider the residuals when they create this histogram, and not just take account of the centroids. So what NetVLAD does is it does not require a fixed set of fixed code book which is pre-learned using some clustering. So actually it sort of trains the clusters end to end via backpropagation. And that's what they mean by this learnable pooling, where they create these, like on the fly, they learn the visual tokens, right? Or the audio tokens for audio features. It's done exactly in the same way. And then you create representations on top of this. And then the other part is about, we talked about a few approaches where we said that interactions between multimodal features as well as from like the same visual features is important, right? And there's a concept of context gating, which is used to do this effectively. So essentially you capture dependencies between the visual activations as well as it captures prior structure on the output space. So if you look at the formula, what it is doing is it's essentially learning a nonlinear sort of a activation by like sort of having this using an element-wise product on these two terms, right? And just to take an example, so let's say if your input has a snow and a tree and a sky, a ski, then you know that like snow and ski are probably more correlated. So when the representations will be trained, or if you look at the activations in the output, you would see that tree as a concept is deviated, right? And this is happening as a result of this context gating module, right? Okay, so the last thing before I close is like there's this recent paper which came up this year, which talks about why multimodal classification networks are hard to train, right? And this is something that we have seen in our experience as well. Multimodal networks are prone to overfitting. One reason is they are these huge networks with a lot of capacity. But more importantly, the different modalities tend to overfit and generalize at different rates, right? And this is very key. And because they overfit and generalize at different rates, training them jointly with a single optimization strategy becomes sort of difficult, right? So they come up with this simple yet elegant approach of gradient blending. What it says is, like instead of computing one loss on the multimodal representation, so here's a simple illustration where, let's say you have these two unimodal representation and then you concatenate to create a multimodal representation, which you are learning in a supervised manner. So you compute the loss on the multimodal representation and you back propagate that. Instead of doing that, so that would create this problem that maybe your M1 will try to saturate faster than M2, right? And so M1 starts to overfit, but M2 is not trained properly. So what they do is, instead of doing that, they compute losses for individual modalities as well as weighted loss, right? And they, like in their training step, essentially they compute this overfitting to generalization ratio, and then they tend to blend the losses for the different modalities based on this ratio. So this sort of improves training for such networks. Okay, so I'm largely out of time, but so in just conclude, multimodal learning is crucial for many key applications in social media companies. We looked at some of the key business use cases which are driven through multimodal learning. There are many challenges, multiple challenges for multimodal networks, and we also looked at video understanding, and there, like again, it's a very promising area because like in some sense, if we can, like video understanding can progress very effectively if we can get good techniques for self-supervised learning. And this seems like a scalable way of teaching machines about real world content without worrying about expensive labeling, right? So that's it. Thank you. So is happy to answer any questions. Thanks is again from ShareChat.
Thank you, Debdoot. It is indeed a very nice and informative talk. So we welcome questions from the audience. Anyone probably can unmute themselves and ask your questions.
Hello.
Hi.
I'm EU from National Institute of Informatics in Japan. So I'm wondering how you process the data parallelly, because as we know you collect the data locally from the different devices, right?
Yeah.
So how you parallel process the data, and how leverage
What
this kind
exactly
of
do you
big
mean?
data to train the model in locally or in the cloud?
Yeah, all of this is on the cloud. So models are trained on the cloud. They are not getting trained on device, at least for a lot of the that is on the device. There are other on-device machine learning use cases on the creation tools front, like we do things on the camera, but none of this is on the device.
Okay. So usually the people would like to share some the video content, the text content, and the audio, the content. So how you can find their correlation? They might fake something when they upload the multimodal data.
Yep. No, so it is one piece of content for the user, right? So for example, like there's this thanks, which is a post on ShareChat, right? So this is an image, right? But you can extract the text from it, right? As thanks. So that text extraction is happening through the OCR system. Similarly, in the case of videos, they are uploading just a video, but you extract the visual component and the audio component and the text component from that video to understand that content. From a user's perspective, they're just uploading one piece of content.
Okay.
Is that answer your question?
Yeah, yes. So what kind of the actual challenges you feel it's very hard to achieve? So you would like to do more for this the big challenge. What kind of big challenge in your ShareChat?
Yeah, I think let's mention some of the challenges. So if you look at all of these are very, very open-ended problems, especially if you look at video understanding. I tried to make that point through that Michael Jackson video, right? Like even figuring out what to label, right? What do users care about, right? Let's say you have infinite resources to do labeling and all of that, right? But like, what are the parts of a video which you'll potentially label, right? So that itself is not clear, especially if you look at a platform such as ours where the topic spread is humongous, right? So like we are getting, trying to get better at techniques where you can learn with limited supervision, right? From the data that you have. So that's where like these self-supervised approaches and different ways to learn from user interaction data is much more appealing, because once you learn from user interactions, right? Like that is how users perceive content, right? If you ask 20 people how they perceive that Michael Jackson video or what stands out, maybe there are 5 different things that will emerge, right? So if you get that understanding from your users at scale, right? Then you would understand really that, okay, for this particular piece of video, these are the concepts which matter, these are the entities which matter, these are the attributes which matter, and like rest of it does not matter, which is not possible technically to do if you sort of get 20 people in a room and say that, okay, I want to label videos, what is the taxonomy, right? So define the taxonomy. The taxonomy itself will be flawed, right? Or it'll have its own limitations, right? And then the act of labeling is much more expensive. Like these are the directions that we are looking at. How can you sort of like in some sense, like one of the reasons for me to come in over here and give this talks is also play to the computer vision community, that a lot of interesting synergies is possible between what is there in recommendation systems and computer vision, right? So if you look at the CDML kind of a paper, that's actually learning from the data is coming from user interactions, right? So the people who work on recommendation systems are masters at like massaging that data to create similarities between like two different posts, right? So that data needs to come from understanding of user interactions, from approaches that have been used in recommendation systems or information retrieval. And the computer vision community or the multimodal community, multimedia community can benefit greatly from that, right? Because like we need to learn at large scale from noisy data on things which matter to users rather than try to of course, you need some degree of sort of confidence in the model with approaches that and you need data sets which are sort of golden data sets to really do the evaluation. But for training the models, especially for pre-training tasks, like models which can excel across different tasks, the more that you can do with self-supervision and using user interaction data, the better it is.
I don't use the share chat, so I wanted to know how many people in India they use share chat the most.
Yeah, so there's like currently it's 160 million monthly active users.
Okay. Whoa.
Yeah. So we like Indians internet population is roughly between 500 to 600. So like almost 1 in 4 people use ShareChat.
Wonderful. Okay, thank you.
Okay.
So thanks, Debdoot. It's a very, very interesting, uh, definitely responses as well to the nice question. So I would like to know, I mean, do you have any ASR system as well? Because you're dealing with a lot of Indian languages.
Yeah, so that's one thing that we are trying to get better at in terms of training ASR systems, and particularly for low resource. That's actually an active area of focus currently. We're trying to sort of build it out.
Okay, great. So yeah, my lab also probably focusing on ASR for low resource languages. Probably we can discuss further.
Sure.
So
Yeah.
let me check. I mean, if anyone else has some questions for you.
Rajiv, can I go next?
Yeah, sure, Subramaniam.
Yeah. Hi, Debdoot. This is
Hi.
Subramaniam from IIIT Delhi.
Hi.
So one of my takeaways from your presentation would be the gradient blending slide. I think we can certainly name a plethora of techniques for unimodal, but coming up with just one single multimodal is hard as of now.
Correct.
So, what are the other directions, other pointers in which research is progressing for such sort of training for multimodal data?
Right. So I think like a lot of the last points that I made, right? So gradient blending is one way to look at it. Even if you look at context gating, even though if it's not talked about in the same terms, but it is about so with gating you can sort of control a lot of how the loss propagates, right? So and that also can help in different parts of the network much better, right? So the other thing, if you look at like the related thing to gradient blending, most of these networks use mixture of experts kind of a training, right? And mixture of experts, essentially the idea is that can you train an ensemble of some parts of like you have different experts, each of which is excelling at exploiting a certain set of feature space, right? And like what tends to happen is because the features spaces tend to sort of train at different speeds, mixture of experts can also help out there, right? So yeah, I think that way, like even though it's not exactly on the same problem, it is a fair bit of relation between, and this is something that we see mixture of experts also tends to work much better in practice on a variety of problems that we have.
Including text as well, right? I think this is showing
Yeah.
video and audio, but including text
Yeah,
as well.
it could be anything. Yeah. So actually, mixture of experts, you need not have multimodal modality. It could be any representation, any set of feature spaces. Mixture of experts could be employed very effectively.
I see. Great. Thanks. Thanks a lot.
Any other questions from anyone?
Hi, sir, can I go next?
Yeah, Puneet, please.
Hi, Debdoot, sir. I'm Puneet Mathur. I would like to know, like, I'm really very interested that ShareChat is using a plethora of and models. So I'm really interested in knowing how ShareChat processes this linguistic data for new sparsely annotated data samples, especially in code mixed and code switched languages. Like I was seeing a few of your examples in the slides where we had Hindi English code mixing, and we also had Hindi along with some other indigenous language code mixed in the same image.
Yeah. So what's your question? Like what kind of models we use for code mixing?
Yeah, like what is this like what is how do you capture all such textual information at such a large because you have a very large volume of data coming in, and how are these models trained? Are all of them trained in a self-supervised manner, or do you have some sort of active learning framework for learning such data on the go?
Right. So what we tend to sort of have is some set of models which can perform on multiple tasks, right? And of course, the representations are fine-tuned on each of the tasks. Thing is, like each task comes with varying amounts of data. Like for the base models, you start off with pre-trained models, which maybe we have, like we also sort of pre-train on like external corpora in Indian languages, right? And then they are fine-tuned. Like largely, all of these are the family of BERT, like those which is largely used. In terms of low resource and like code mixing, etc. So like we tend to sort of group different languages by these common scripts, right? And in each script, we try to sort of also so again from task to task, the text representation that is being used or the model is different. Certain tasks you would have language specific data, language specific models. Certain tasks will have language agnostic models, right? And so one trick that I mentioned here is transliteration helps to sort of connect uh, words or tokens from different languages into a common space. That's one technique that we can use to increase the data. So let's say there is there's Oriya and there's Hindi, right? Hindi, of course, your models will be trained much better because you have more data available. But Oriya, you may not have that much to train your model. So if you transliterate Oriya into Hindi, right, and train on a common corpus, and then if you sort of see the embeddings, they tend to make sense in a lot of cases. So wherever there's data available, you'd go in with language specific models if there's value in getting that thing. Otherwise, you would have these some sort of common pre-trained work across languages. Did that answer some of your
Got it.
questions?
Thank you so much, sir.
Thank you.
Yeah.
Okay.
So we do have room for another one or two questions. Anyone?
If I may go next, Rajiv.
Yeah, please.
Hi, thanks for the excellent talk, and definitely, brings open a lot of challenges that real challenges that exist. Do you also face bias issues in the data sets, and if yes, how do you deal with it? And a secondary question is, are you planning to put any data sets out given the size of your platform?
Yeah, so like, can you clarify what kind of bias you're talking about?
Well, a huge issue that we see. I mean, I'm from Adobe Research. That we see in the data sets that we use and public data sets that are available is it lot of the data sets that YouTube 8M, for instance, in terms of demographic mix, it's just not there. A lot of the face data sets have the same problem. A classic example is that the generic data sets don't work for Indian faces, for instance, or Korean faces or Chinese faces. Do you see such issues in problems in your domain too?
Yeah, absolutely. Yeah, so like those kinds of issues are always there. So like that's where I think in most of these applications, when I talked about the data needs to be fine-tuned on your own data sets. Without that, pre-trained models which are trained on maybe Western data sets will not work that effectively. And sometimes,
and are you planning?
and a lot of times it's not also relevant, right? So for example, let's say, there are lots of these issues which are like one example which I don't know, which you guys may relate to. So you have so many gods and goddesses in Hindu culture, right? Can you identify each deity, right? With like, if you use a pre-trained FaceNet model, it won't do a good job at all, right? So we have so many different like idols of Krishna Bhagwan, right? But if you talk to a Hindu, he'll identify and be able to recognize all of the faces as the single entity. And like that's a challenging problem. Like that's a kind of a very, very specific example which you would not like a pre-trained model will never work.
Thanks. And as a follow-up, are you planning to put any data sets out?
Yeah, we'll still work on the data set. Like we are putting some of the models out. So for example, the OCR model, we are putting out pre-trained OCR models for the Indic languages. So we are definitely in the process of putting out pre-trained models. Opening up data sets is something that we'll need to work through more.
Thank you.
Okay, so we have one question from Jerome. So someone please unmute Jerome. Aryan?
Hello, am I audible?
Yeah.
Hello, thank you, sir, for this presentation. I just had a question about the languages part. Does the model that you train on interfere with the slangs and the dialects of the language? Because the proper data sets that are available would be strictly consistent with the grammatical part of it. Does the slang also interfere in the audio?
Hey, you're not very audible. Rajiv, can you hear him fine? Hello.
So I guess there is a lot of noise behind him, so even I couldn't hear him.
Hello.
Can you please repeat your question, Zero?
Can I just write my question? Would be actually
Yeah,
all right.
please.
Yeah, sure. You just type it in the chat.
Sure.
Okay. Are there any other questions in the meantime?
So we have room for last question. So anyone?
Yes, there is a question from Shivam in the Q&A section. If everyone can see, I'll just forward it.
Probably Aryan, you can just read the question.
Okay, so the question is, there is often multiple speakers and audio and video data, which leads to the cocktail party problem. What kind of models do you use to identify each speaker or the most important speaker from all speakers?
Yeah, that is not a problem that we have looked at. But having said that, the background noise, there are sort of techniques that we are looking at to eliminate that. But in terms of who's the most important one of all of them, as long as and this is in the context, the only application that we have is in the context of ASR, right? As long as we get the text, we've not focused on that particular problem of identifying the key speaker. It wasn't too important for our use cases. Okay.
Okay, so probably I request everyone to probably send their question through email, and hopefully Debdoot can help us answering that because we are running out of time.
Sure.
So I would like to conclude the session, and I would like to thanks Debdoot and all the attendees. Thank you so much for this is indeed a very useful session, and thanks Debdoot, and thanks for making us a very useful keynote.
Cool. Thank you for the opportunity. I just typed in my email, debdoot@sharechat.com. Any other questions, please feel free to send me over email and reply. Thank you. Thank you so much, Rajiv. Thanks, everyone.
Thank you so much, everyone. Bye bye. Have a good day. So we will be starting next session from 10 a.m. So feel free to attend the track whichever you like. Thank you so much.